Yeah, hello everyone. I also want to say that I'm really grateful to the organizer for allowing us to present those papers. It's, the previous 2 years were a little bit sad that we couldn't do that, and I'm really happy to be here to present the work of my student Max and also my co-worker Bettina on FIDDLR, streaming reuse with concern-specific modeling languages. So in software engineering in general, one of the big challenges is complexity, and we have been trying to reduce complexity with many means possible, and we have lots of tools in our bag of tools. In particular, one is abstraction, and in model-driven software development, we're using models, we're building models of the systems that we're developing, and the main, I would say, technique we're applying is abstraction. So we focus on some details depending on which level of abstraction we're building our models on. I focus on some details and we omit others, and then we can analyze the models and we can transform the models and add more details until we find some solutions. So that's one thing MDE is really good at. And another thing that MDE can do pretty well is a separation of concerns. So the main idea is we focus on some aspect of our system, and again, in MDE, sometimes we even develop special languages that focus on certain properties more than others, and we can specify different viewpoints of our system. By using the most appropriate languages to focus on those properties, we can really separate the concerns well. Another aspect that is really important in software engineering is reuse, and I've been working on that for quite a while now in my career. And there we are not so good in modeling, I would say. If we want to reuse models just as is, that is a good thing if they happen to apply directly. But if we only want to use parts of a model, it becomes more difficult. So here, for instance, let's say we have a bridge, a model of a bridge. Let's say we want to only reuse this beam. So then that's more tricky with the standard modeling technology, and that's where I would say maybe 20 years ago, the first papers on aspect-oriented modeling came out. It's a technique that allows you to do a partial model reuse, and in particular, one technique that me and some of my coworkers have been working on called concern-oriented reuse. We have been using aspect-oriented modeling techniques to do exactly that: how to package models in a reusable way, and our reusable units are called concerns. And what we do with concerns is we prepare everything so that a concern user can really easily reuse whatever is packaged in this concern. And for doing that, we have these three interfaces. One is called the variation interface, where the user picks one of the variants of the concern that is the most appropriate for his specific needs. And then there's a customization interface where the concern user can adapt the variant that he picked to the specific reuse context. So if you want to illustrate it, I try to illustrate it here with the picture. So if you have this beam, first you would pick which variant of the beam, maybe a beam with lots of connecting pieces to make it very stable. And then afterwards, if you want to apply it, for instance, here to build something new, not a bridge, but in this case a tower, then you need to somehow, shift it, move it, and then finally, to get it all together to build your model. In this case, you can see the beam has been reused many times. You need some tool that can do that, and in aspect-oriented modeling technology, that's called a weaver. So you need to have a model weaver that can do that. So this is great, but there are limitations. In particular, of course, if you want to use aspect-oriented modeling technology, then your language has to provide a weaver, and it's actually not trivial to create such weavers. Again, in my lab, we have been creating weavers for several modeling languages, and it's a difficult thing to do. But even if you have weavers, then you can run into problems because, in particular, if you take some, let's say, complicated concern and you would like to package that one in a reusable way, you might need many languages to express the properties of that concern or the solutions you might need some structural languages, some behavioral languages. So you need many general purpose modeling languages to express a concern nicely. And then, so that's again complex. And then if you want to reuse that concern in your specific application, then that can cause problems, because if the concepts of the concern don't align well with the concepts of the general purpose modeling languages in which the solutions have been expressed, then you create this accidental complexity where you have to, constantly, I guess, switch between domains when you want to apply your concern. So that is a problem. And the general solution, what we've been doing in the model-driven engineering world for a while, is whenever we have a specific problem and the general purpose modeling language doesn't fit that problem very well, is we create a new language, a domain-specific modeling language, where we have the concepts that are we express the concepts that are tailored to the domain in the language itself, and then again, it allows the user to maximally focus on the properties that you want to express. So that's the general idea. It has been very successful in the past, and the main message of our paper is we should do exactly that also when we build reusable units. So somehow we call those concern-specific modeling languages. So these are languages that you're building specifically in order to make something that you want to, some entity that you want to make reusable. You're building a language for it so that you can easily that you will be able to streamline its reuse maximally. So that is the main message of this talk. So the rest of the talk is just basically how can we make this easier for a concerned designer to build such a language and integrate it with this reusable unit? How can we make this easier? Because this is a definitely complex thing to do. And I'm also going to illustrate how we can make the reuse for the concerned user a lot easier when we have such concern-specific modeling languages. So this the title of our paper is called FIDDLR because we propose this framework for helping the concerned designer create and package a concern with a modeling language. So it's an abbreviation for framework for the integration of domain-specific modeling language for concern-oriented reuse. And it basically splits this complex task, this complex thing to build a language and package it with a concern into three distinct separate tasks that can be done by the designer. And by doing it like that, we can provide some generic tools that will help the accomplishment of those three tasks. And also we can reuse existing tools that we already have in our model-driven engineering tool chain, or if we have some aspect-oriented weavers that are already there, we can reuse them. Now let me first, so that was all very, I would say, high-level and abstract. Let me get concrete. So I want to talk about one specific concern that for which we developed a prototype. The concern is called Restify. So the idea is we have, let's say we have some desktop application that we already have. As you can see here on the top, let's say we have some jar file, we can run that. And we would like to now allow this application or the functionality that this application provides to be accessed over the web through a REST interface. So ideally, we would like to take our desktop app and apply the Restify concern to it, and then get a REST service that can be called over the internet. So traditionally, doing that is not a trivial thing to do. So there are existing frameworks out there that you can reuse. For instance, the Spring framework allows you to define REST services. But to do this conversion, it's a complicated thing. You have to, first of all, make a choice. Spring is not the only choice. There's other, Apache CFX is another technology you could use. So depending on which technology you use, you have to download the right frameworks, obviously, but then prepare launcher classes and add some boilerplate code. Then you have to think about your REST interface that you want to expose, and you have to go into the code and put annotations. In Java, the way it works in Spring is you put annotations to the methods that you want to expose, and in those annotations you have to specify the URLs that you want the user to use. So it's a complicated thing. And there's also anti-patterns, some naming conventions that you should follow or that you should not, things you shouldn't do when you build the REST interfaces, and so on. So it's a quite complicated thing. So wouldn't it be nice if we could actually do this by working at the right level of abstraction using the concepts of a REST interface? Now if you think, for those of you who know standard, let's say, general purpose modeling languages, or if you think of the UML, you would say, oh, which UML modeling language would be ideal to express something like a REST interface? Then you will also see that that is actually no good match, because if you think about a REST interface, you want to build some sort of a tree, or it's a hierarchy, like a tree structure with your URLs, and there's nothing really in UML that does that. So again, that's a reason why, what I said before, it's a misalignment between the concepts of the concern and the general purpose modeling languages. Okay, so how could we simplify that? So ideally for the concerned user, wouldn't it be nice, instead of having to deal with all this low-level things when you apply, for instance, Spring, would be the first thing you want to do is really make the choice of what technology you want to use. And choices typically can be expressed with something like a feature model. So wouldn't it be nice if we had a feature model, for instance, like this, which would say, okay, we have the restify concern, and this concern that we built, actually, that's our prototype, supports 4 different lower level implementation frameworks. So yeah, you can use Spring or Jersey or Apache CFX or JBoss, rest easy. So from a user point of view, you simply would like to make a choice. Now you would like to say, oh, I want to use Spring or something like that. Now, how would you know whether to use Spring or Jersey? Well, they have trade-offs. There might be performance reasons why you want to choose one over the other, or compatibility reasons, or maybe I don't know, memory usage of one is higher than the other. So you could imagine having behind this feature model also some goal models or impact models that would allow you to express which choice, what kind of non-functional properties do these choices affect, and it could make it very easy for the concerned user to make a good choice. So in our case, concern-oriented reuse, what we've been working on before this work, we already have integrated these feature models and these goal models into our approach. So this came out of the box. That's not something new that we did for this paper. So step 1, basically here, that was already provided by Core. But now step 2 is this is now where the CSML will be very helpful, because like I said before, for instance, if you're using Spring, you have to place annotations in your Java code at the right places, and you have to type as a string the URLs that you want to use for exposing your different resources. So you're working at the level of strings, and it is scattered. These strings are scattered throughout your code, and you're not really building a resource tree. So this is exactly where we came up with this CSML. In this case, we call it RESTful, so resource tree language, where we're expressing, as you can see here, a tree. In this case, it's a bookstore application, where we say, okay, the root is called bookstore, and then, for instance, if you go /ISBNs, then you can, these are the ISBN resources, and then you can give, for instance, a specific ISBN for a specific book number, and then if you put a get on it, then maybe you get the information about this book. So you can see here we're modeling the tree, and these 4 circles you see are the get, put, post, and delete requests that you can send. And the curly brackets represent a dynamic path where you can put a specific ISBN number here or a stock location if you want to know, for instance, what are all the books that are currently at the Montreal bookstore. You could go bookstore/stock location/Montreal and get. So you really, here is the advantage of the CSML. Note that you're building a tree and you're focusing maximally on that task, which means that you're a lot less likely to make mistakes. Now, of course, you have to connect now. There's a place where you need to connect the tree and your actual code. And here we propose that you have to just specify those mappings. So in our tool, you can open so two windows if you want. On one side, you have your RESTful tree, and on the right-hand side here, you can see a class diagram, for instance, of the application that exists. So you can so extract the class diagram from your existing Java file, and then you see these different Java classes that implement a certain functionality, and then you can simply map. You can say, oh, this get request should map to this method call, or for instance, this dynamic fragment, like you can see this curly brackets ISBN, can map to certain input parameters. So you're mapping the methods, and you're also mapping the dynamic fragments to get the parameters. And that's it, basically. So that would be all. And then you can, the idea is then the concerned user can sort of press a button, and then behind the scenes, the tool will use all the existing MDE and aspect-oriented tools to compose the application and generate the final code. So I hope I convinced you that for a concerned user, this would be really nice, so to restify an application like that. Now, what does the concerned designer have to do to make this possible? So this is a complex activity, but like I told you in FIDDLR, we can decompose this into 3 specific tasks. So first of all, of course, we have to have implementations of those different technologies. So of course, we're going to reuse the existing code, we're going to reuse the Spring framework and so on. So that's one thing that needs to be done. We need to design the language itself. So our prototype supports meta model based languages. And so in this case, you have to create a meta model for this language. And if you want to have a nice editor, you need to create a nice editor. And then finally, you also have to provide transformations that take these mappings that I've shown before and actually transform the information that you get from those mappings into information that can then be used in the GPMLs to continue at that level. No? Because like I told you, we assume in the model-driven engineering toolchain, we already have, for instance, code generation tools that can generate code, for instance, from existing models. So what we need to do is we need to have a transformation that takes the information from the concern-specific modeling languages and translates it into general-purpose modeling language information that can then be continue to be used. So these are the 3 steps. Now, in general, if we don't think about Restify, then we need to do that. So for any concern, we need to realize the concern, its properties, its behavior, its structure using GPML concepts. So that's the one step. We need to provide a meta model for the concern-specific modeling language. And then we need to work on model transformations that take those mappings from the CSML to the GPML model elements and map them or transform them into mappings between the GPML, between those GPML realization models that are actually implementing the concern and the GPML realization models that the application provides. Yeah, and I mean, there might also be some configurations that have to be done. You know, like I mentioned before, if you're using certain frameworks like Spring, you know, some of those mappings will also have to be afterwards transformed into certain Spring configurations that have to be set at startup. But these are the, well, I mean, I know that sounds still very complicated, but there are 3 well-defined tasks, and then all the other MD and AOM tooling can be reused. So that is the big advantage of FIDDLR, and if you want to know more details, you should look into details of the paper. Yeah, so I'm already at the summary. So it's really, I hope I convinced you that concern-specific languages can make it a lot easier for the user to reuse a concern. So that's what they are meant for, to make it easier for the user. Having a new language makes it, of course, harder for the concern designer, because you need to integrate that language with the other MDE tooling chain. And for that, we created FIDDLR. So instead of having to do this in an ad hoc way, it's split into those 3 clear tasks that I just explained: the actual concern realization, then the language definition, and finally the transformation of the connections that the concern user provides into mappings between the general purpose modeling language realizations of the concern and the application. And we can reuse the MD tooling and the AOM tooling. For the concern user, the whole reuse process is becomes very structured. You first make the decision about the specific variant that you want to be using, and then afterwards you get this language that allows you to maximally express the new concern that you're adding to your application. In our case of Restify, you can build this beautiful resource tree in the most appropriate language. So you can do all these, I didn't mention that, but our tool can do all those checkings, obviously, that when you create mappings that you can't map, you can't map a get to some method that if you haven't specified certain parameters, or if you change a mapping, then it will check again that the parameters are still all that the parameters can still all be matched, and so on. So there's lots of checking that you can do. So that's a huge advantage. And then something complicated like in Restify can be really simplified, where you have these clear steps. So instead of having to work at different levels of abstraction that don't match your concern, like the example in Spring, where you have to work with annotations in your Java code that are sprinkled over your whole application. Yeah, that's it in the continuation of this work. So as you know, this work was a paper from last year, so we have actually already continued, and we are just now completing a user study where we have had 28 developers we asked them to restify applications with our tool and our XML and without, and we're currently writing up the conclusions from the study. If you're interested, you can talk to me in the break of what we already know. And of course, we want to apply FIDDLR to other concerns. For instance, currently we've started working on authentication and see how we can build a CSML for that. That's it. So I'm very happy to answer any questions you might have.
So you talked about having those places where the user can take the details, for example, about the technology. Have you thought about some way to have like defaults for those decisions to sort of adapt, because maybe if you add one choice, that is, I don't know, if you use Tomcat, then some other choice, the default should sort of change because it makes more sense. You know, like when you have a big network of choices, have you thought about how to, you know, reduce it and enlarge it and automate it so that when one select one, other suggested or more defaulted?
Yeah, thank you for that question. It's a very interesting question. So, not specifically in this work, but when we work on core in general, where you have these, well, this is the idea, you know, that the concerned designer comes up with several variants and you express in the feature model. So there might be, like you said, already certain dependencies. If you make a certain choice, you have to make some other choices. And these choices can be expressed in the feature model. So you can have these cross-tree constraints. You can say this feature requires this feature. So that's something, if the concerned designer knows about that, that's something to do. But you're right, there is this problem of, for instance, an overwhelming amount of choice. And so, again, I didn't show you these slides, but I mentioned that you can have this impact model that is behind the feature model, which expresses, for instance, like we have done certain concerns on one, for instance, on security, and then we have, for instance, impacts behind this, for instance, the level of security. Certain things might be more secure, you know, password-based security can be not so secure than biometrics or something like that. But then you might also have something else like user convenience. Biometrics might be, depending on what kind of biometrics, a lot less convenient. So you have different implications of certain features. And then you can imagine, instead of making a choice where you actually choose features, you could say, oh, for me, security is the most important. And then you could have a tool that will, you can sort of rank your saying like security is the most important, user convenience is the second most important. And then you could have some automatic selection, maybe, or at least a proposition, and then you can still play around with that instead of having to explore.
So I'm also curious, maybe a little bit on into your future work. Have you asked these people, the users, how easy it is to debug? Like whenever we add abstraction over another abstraction over another abstraction, debugging is what, like we increase efficiency in general, but debugging can become a little bit of a...
Okay, the debugging question is a great one. I'm going to avoid it by saying it's a general problem maybe with model-driven engineering. You know, how do you debug it? So of course, I mean, I've seen, you know, in SLE in particular, there's people who work on debugging of models, and they have done some really cool stuff. So if you can actually connect the running application with your models, it's kind of beautiful. So I've seen some really good stuff working. Now, if you add this layer of abstraction, where everything is cross-cutting, it can become a lot more difficult. So I admit that we have not worked on debugging of this, and you're right. In general, I mean, I've written a lot of aspect-oriented code, and already there, the debugging becomes more difficult, you know, if you have aspects and so on. So it's a challenge.
Right. For the SME community, that could be. Any other questions? Maybe we can prepare for talk.
Thank you very much.
Thank you.